Hello everyone, today we're going to be talking about chi-square. Previously I made a video about how to carry out the test on the TI-84. If that is what you're looking for, then go back and look at the previous video. In this video I'm talking about what chi-square is, and what sort of context it appears in. To help illustrate this distribution, I will use a colored ball example. Now, we've already done this in the context of a proportion test, but the problem with a proportion test is it will only tell you if a proportion of one color of ball is wrong. We want a way to tell if any proportion is wrong. So, the idea is simple. We start with a bag of balls. And the idea here is, one second, while I draw this nice bag, and by nice what I mean is barely functional work of art, we'll call a bag. There we go. This bag starts with several different colors. Now, these could be any sort of color, but for this example, we're going to assume that they're red, green, yellow, and blue. So, as a specific example, suppose that our bucket happens to have the following proportions. 20% of them happen to be red, and that 30% are green, 40% are yellow, and 10% are blue. Writing that over here. So these are our true proportions. That red is 20%, that green happens to be 30%, yellow is 40%, and blue is 10%. Now suppose we take a sample from this bag, a sample of 25. Now this sample is obviously going to be unlikely to match our true proportion, but we really aren't interested in that. Just like with other tests, we really want to know how far away is our sample from the true proportion. So we start with determining the values that we should have had, the expected values. Now, the expected values are found pretty easily. We simply take the true proportion that we have here, and we're going to multiply them by the sample size, which, as I said, in this case, we're going to assume that sample size is 25. So that means that the true amount of red balls we should have would be 0.2 times 25, which we could go ahead and do that math inside of our nice calculator. It's just simply 20%, so 0.2 times 25 gives us 5. And we could continue this and continue this as well. So we have 0.3 for the number of green times 25, giving me the number of greens, the number of yellows times 0.25, and finally the number the percentage of blues times 25, giving me my three values, 5, 7.5, 10, and 2.5. So going ahead and writing that out, that'd be 5 for green, we have 7.5, for yellow we have 10, and for blue we have 2.5, giving us, these are our true values. This is where we expect. Now, suppose for a second that our actual sample, the one that we grabbed from the bag, happened to instead look more like this. So for these we'll use a hat to represent this is my sample value. And the number of reds we had was 4. The number of greens we had was 6. Yellow, oh sorry, not 6, 12. The number of yellow is 6, however, and the blue happens to be 3. Now you might ask this question, how far away are these numbers from what we should have had? How different is this from what we would expect? And for this, we really need an equation. Now, this equation I'm going to write out is what's called chi-square. And this chi-square, chi, looks a little bit like an x. It's a little curvy x. And the equation looks rather similar to something you've seen before. It is the number of observed minus the expected squared divided by the expected. And if we sum this across all categories, So all the differences between red, green, yellow, and blue. If we sum across all of those, that is chi-square. And you'll notice this equation looks awfully similar to something you've seen before, namely variance, which you'll see the original equation looks like this. Once again, we have a square difference divided by a number, giving us the variance. And so once again, notice how very similar these two equations look. And that's because they're doing the exact same thing. They're trying to give us an idea of the average squared difference. And so this right here is the equation we'll be using for this chi-square. So let's go ahead and get through with that. So the very next thing that we're going to be doing is talking instead about Python. Now, Python is a programming language. Now, you don't need to know how to program. This is just to give you an example of how I'm going to do this. What we're going to do is we're going to perform a simulation. Now, the simulation method is written in Python, and it's going to simulate drawing the balls from the bag. You'll notice I've already written in here the proportions, 20, 30, 40, and 10 for each of these balls. I've also sat there and written a large portion of this program. What I've done is I'm going to tell it to draw 100,000 of these samples, and the sample size will be 25. And basically what it's going to do is it's going to do this over and over again with the intent of drawing all these balls and being able to tell us how far away we'd expect this to be. So if we just did this randomly and assuming this was the true distribution, how far away should we expect it to be on average? And so all of this right here is just drawing the balls. This right here just collects them into a single variable so we can actually deal with the balls. And finally, this is the part where the magic happens, where the chi-square is calculated. You'll notice that it starts out by taking the difference between the number of observed and expected. It then squares it with this nice little function here, and then it will divide it by the number of balls that were expected, and then it adds them all together through every single category. And once it's done, it then adds that to a list, which eventually I'll take that list and put them into a count, smooth out the data, and make a plot. And all of this stuff is just so that everything looks nice and pretty, because I want this graph to look good and clean so it's clear what's happening. So let's run this. Let's see what it looks like. After 10,000 simulations, this is what you end up looking at. And you'll see that this graph happens to have a particularly interesting shape. Namely, this graph seems to be a bit kind of uncommon when you're close to zero. It's real, as I said, it's really unlikely you're going to have it be exactly the same. It seems to shoot up up to around here with an average distance of 1, and it starts to come back down. So it seems to suggest that this is the approximate difference that we should expect. Now, let's go ahead and see if we can make this a little bit clearer. We're going to go ahead and increase our sample size. A more clear image. So going ahead, running it again. So what you see here happens to be the exact same graph, but much smoother. So this time, this graph, as you'll notice, has a much smoother curve. And once again, we see the exact same shape we saw before. It starts to go up from right here, peaking somewhere around 1, and then it comes back down, eventually tapering off. This is what is called the chi-square distribution. And it's not a normal distribution. This is not a normal distribution. It's not related to the normal distribution. It's actually completely different. In fact, the chi-square test does not require normality. That's right. You do not need to have that particular requirement. You still need random selection. You still need everything else you needed in order to keep independence. But you do not need normality to run a chi-square test. This test will work even if you cannot assure normality. This is what makes chi-square what's called a non-parametric test. Whereas all other tests I've covered so far, that would be the standard means test with t distribution, and of course the z distribution test involving proportions. All of those are parametric. but chi-square is called non-parametric. There are many other non-parametric tests, and there's a lot of interesting properties for them, but all of that is a bit beyond AP, and so I'm going to go ahead and cut off the video here. I hope that this video will find you well, and I hope that you have a good day.